All righty, good people. Here is video number 3 as we work with the accumulation of rates of change and what that represents, and also how to estimate areas under the curve for graphs that are not going to produce nice geometrical shapes for which we know formulas for the area. So the second big idea is this. There's several methods to approximate area under the curve. We're specifically going to deal with two shapes to do that. The first shape would be with a rectangle, as you saw in the previous video. We call those Riemann sums, and you're going to see shortly why we call them Riemann sums. And the second shape we're going to use primarily to estimate is the trapezoid. And we saw that in the previous video. So if I go back in time here, we can see that in the previous video, we built these rectangles as a way to approximate the area that we truly wanted. We really wanted the area under the curve. That would be the area that's in blue here. But we couldn't find it because of the curve, so we approximated that with our rectangles. And in the previous video, we wanted to find the area under the curve here in blue again, and we approximated that with our trapezoid in purple that we created in order to find the area and establish, I guess, an upper bound for the area in blue. So as we come back, there's some things we need to know whenever we're building rectangles to approximate. We need to know a couple of things. Number one, we need to know how many rectangles we're going to create. Depending on the number of rectangles, our answer is going to be slightly different. And then the second thing we need to know is what type of rectangles are we going to create. And when I say type of rectangle, that's going to depend on where we measure the height. Are we going to measure the height on the left side, like we did on the previous example? Are we going to measure it on the right side? Or are we going to measure it in between at the midpoint? And so we have different types of rectangles: left rectangles, midpoint rectangles, right rectangles. But all of them are called Riemann sum rectangles that will approximate. So let's dive in and let's take a look at, again, this is the same curve, VQ of t. Remember, we had established that VQ of t has a formula. So our job now is to approximate the area under the curve. And you know what? I'm going to change it to blue highlighter here. So this is what we want, right? And as we notice that we can't use a geometry formula, we're going to use a left Riemann sum with one subinterval to approximate the area between the curve and the x-axis, or in this case, the t-axis, from t0 to t2. One subinterval. So we're only going to treat this as one big rectangle. It's a left Riemann sum. And what that means is if I start at 0 and end at 2, and we're just going to make one big rectangle whose width is 2, right? Because I'm starting at 0 and I'm ending at 2. The height of the rectangle is not going to depend on the right side. It's not going to depend on the midpoint. It's going to depend on the left side. So the fact that this is a left Riemann sum means within this width, I'm going to use the left endpoint as the height and then make my rectangle in that fashion. Now, if I look at this example right here, I can clearly see that this orange rectangle that I'm about to calculate is definitely an underestimate for what I want, but it is an estimate for that shaded region. So how do I do that? Remember that we always multiply the height, or I guess I'm going to call it the length times the width, right? So we're looking for, technically, we're looking for this, as we saw on the previous set of videos. We're really looking for this because we're looking for the area under the curve. How do we find that? By multiplying the length times the width. One of these we know for sure. Well, actually, both of them we can find for sure. But we're going to approximate this using what we know about the width, and the width is 2, times the height, and the height in this case is just 1. Now, I'm going to write 1, but remember where this 1 came from. The 1 came from this formula. 0.5 t squared plus 1, because if you do 0.5 t0 squared plus 1, that's how we get this. I can definitely see that the height is 1 just by looking at the graph, but I need you to know that that came from the fact that we knew this formula, and if you substitute 0 into the formula, we get 1. And therefore, we get that my approximation is 2. Now, you and I both can see that this is a little bit under the shaded region, right? The shaded region in blue is what we want. This orange region that equals 2 is not enough. So it's a lower bound. But this is the left Riemann sum rectangle with only one subinterval. There's only one width to approximate the area. That's what we did in example 1. When we look at example 2, now we're going to still use a left Riemann sum, but this time we're going to do 2 equal subintervals. So if I'm starting at 0 and ending at 2, if I'm starting at 0 and I'm ending at 2, then this is going to be a subinterval and this is a subinterval, right? My interval from 0 to 2 is going to be broken up into 2 equal parts, from 0 to 1, from 1 to 2. That means my width is 1. I'm going to start to call the width the delta x. And the delta x, or in this case, the delta t, is going to produce the width, the change in t here from 0 to 1, that's 1. From 1 to 2, that's 1. But now, because I have 2 rectangles, I'm going to have to worry about what the heights are. So I'm going to draw the first rectangle. Since I'm doing a left Riemann sum, I'm going to start on the left side. And I want to go all the way until I hit the curve, because then that's going to determine the height of the first rectangle. And there's my first rectangle there. And then I'm going to go to the next subinterval. The next subinterval starts at 1 and it ends at 2, but I'm using the left side, so I'm going to start at 1 and I'm going to go all the way up until it hits it and then go over, and that's going to determine the height of the second rectangle. So if I call this A1 and A2, the area of the first rectangle plus the area of the second rectangle, then I can say that the integral from 0 to 2 of this function v of t dt is approximately area 1 plus area 2. Now, if I were to shade that in, would that shade in everything under that curve? Well, no. But it's a little bit more than what the previous thing was, right? And mathematically, or I guess numerically, we can figure it out, that the area here for this first one, the height was 1. So I'm going to say v of 0 times delta t. V of 0 is 1, delta t is 1, so this first rectangle is 1. And that should make sense because look, if you look at the base is 1, the height is 1, so 1 times 1 is 1. Plus, this is going to be v of 1 times delta t. Delta t we know is 1. V of 1 we don't know, and I don't want to estimate it. I want to use the formula that they gave me. So I'm going to say 0.5 times 1 squared plus 1. That is our formula that's going to determine the height. The height is 1.5, so 1.5 times 1 is 1. And so therefore, this equals 2.5. So this area is a little bit more than the previous one, and therefore it's a better approximation. So far, we're looking at the same blue shaded region under the curve. On the first example, we used 1 rectangle. On the second example, we used 2 rectangles, but it's still between time 0 and time 2. Our value is getting closer and closer to what we want. So I'm going to pause here. The purpose of this video was to walk us through how we build Riemann rectangles, Riemann sums. Riemann sums, we're just multiplying a length times a width. The length is the height based off of the function, so it's kind of a v of t. And then the width is the change in the horizontal quantity, which is delta t or delta x or whatever you want to call it. But this is how we're going to approach the approximation. Is it a good approximation? We'll see. Let's look at the next video and we'll check out what happens when we do right-sided rectangles.